Thanks everybody for signing on. I'm coming to you actually from the University of Akron. There is a conference going on, MAC conference, of which UB is a member of the MAC schools, and so I'm at a conference here, but that's the background if you're wondering, like, hey, I never saw that at UB. So this is a shot of the CTSI building. So UB has a Clinical Translational Science Institute, and that's the building there. The website is there, and we have several aims that are associated with the BERD core. So the BERD core is one of the cores within the CTSI, and those are our aims. And here's a brief outline that sounds like you've already gone through. My plan is to develop a statistical analysis plan, or talk to you about what the statistician or biostatistician is going to be looking for, and really what they should be asking you and what they should provide you with when developing research plans, whether it be for a grant or for other proposals. And so these are the learning objectives that I've used in the past, and I won't read through them, but I want to get at the overarching goal. Think like a statistician regarding your experiments, or at least understand what a statistician will be thinking about regarding your experiments. And so obviously in an hour and 20 minutes, we're not expecting the audience to become statisticians, but to get a feel for what the statistician is going to be thinking about and what they're going to be asking you about is really the goal of this kind of a talk. And it can be broken down into those 4 learning objectives, but that's the overall goal. And so first off, motivating this. Why is a statistical plan or method important? And I've got a few slides here to try to make analogies or connections as to why developing the stat analysis plan is important. And I think this first quote here, clear writing is clear thinking. And I think if you're clearly able to relate what your data is going to be out of a proposal or from, say, a grant, I'm going to be framing this a lot in the sense of writing a grant. And so writing a grant, you're going to tell them what you're going to spend their money on and the data that you're going to gain out of that. And if you have a clear idea of what that data are that you're going to gain, then I think that proposal comes across with clear thinking. And so being fully aware of what data it is you want to gather, why you want to gather it, and then how you're going to analyze it really is going to provide the reviewers with, hey, this person clearly has thought about these experiments from beginning to end and knows what they're going to do with it, the results. The People's Court was something I remember as a child watching, and Judge Wapner was famous for one of the lines of get it in writing. If there isn't a problem, it's not a problem to get it in writing. But if there is a problem, well, wait a second, there won't be a problem because there's a written record. So getting that data analysis plan in writing, I think, is really important, because you can always go back to it. You can always refer back and say, oh, what were we going to do with that data again? Oh, there's a plan, we wrote it up. And so I really think that hammers it home that sometimes grants are written a year before they're funded, and then it's another 2 years or 3 years before you've actually gathered data. Over that time, how do you remember what it was that you wanted to do with it? Well, let's go back to what the grant said and what the data analysis plan said. And having a well-developed statistical analysis plan means that there's enough detail there to say, oh, I know exactly what we're going to do with this data. And so if it's in writing, it's really going to prevent a lot of problems that could happen downstream. A last why, here are guidelines from JAMA on methods and statistics. And so if you think the next step after grant writing and funding and research, and then its dissemination of the ideas or the conclusions, the dissemination part is going to expect that the methods section has stat methods that are described importantly with enough detail to enable the reader to reproduce the results. So it can't just be a 2 or 3 sentence thing. All data were analyzed by means and standard errors and so on. That if you're shooting for premier journals, then they're going to expect statistical methods sections that are well developed to the point where you could hand this to someone independent from the original study and they could reproduce those results. So I think there's certainly strong motivation as to why the statistical methods and statistical details should be fully developed. So I've also gone ahead and translated these learning objectives into really what that data or what that means in terms of probability and statistics. And so there's the first line about understanding basic concepts about randomness and variability. That's really random variables. Bullet point 2 has to do with statistical models. Then from 2 to 3 is where we switch from the model to gathering the data and making inference on those models. And so you'll often hear probability and statistics spoken of in exactly that order, joined by and, but and the reason for that is because probability comes first. What are the probability models that we're thinking about fitting to our data? And then the statistics part is actually the fitting of those models to the data. And then the last step is knowledge. So we'll have the math equations and the Greek letters and so on, and the p-values and all those things, but then where does the knowledge come from? So how do we translate that back into knowledge about the scientific domain and the experiment and so on? So probability and random variables, we'll go through all 4 of those bullet points briefly. Probability is the mathematical language for quantifying uncertainty. And that uncertainty stems from imperfect data. All sciences have imperfect data. We're always measuring things with some noise associated with them. We often can't measure exactly what it is we want to measure, so we measure a proxy of those variables. I live in a research area where we study gene expression, and gene expression is measured by oftentimes measuring fluorescence. And so we try to make the mapping that the amount of fluorescence can measure the amount of gene expression, but that's maybe true for some genes, but maybe not true for all genes. And so the first recognition is that all sciences and all data are likely to be imperfect. And so what does it mean when we're going to talk about random variables? And in a very sort of toy experiment, the idea behind random variables, or I hope to illustrate what is meant by random variables. And this should really be the first thing that you think about in what your experiments are going to be. In other words, what is it that we're going to be measuring? And so the uncertainty in an experiment could be captured with the sample space. So if you open a statistics book or a probability book, they'll often start chapter 1, sample spaces. And simply put, the sample space is the set of all possible outcomes in an experiment. Points in the sample space are often called realizations or sample outcomes. And so, for example, we might flip a coin twice. Heads denotes, or H denotes heads, T denotes tails, and the sample space from that experiment could be denoted in the set below. So HH means you got two heads, HT means you got a head first, then you flipped again and got a tails, TH tails first, and so on. So that sample space, in a way, is all of the possible things that could happen in your experiment. And so that's why it's the starting point of any kind of an analysis. What are the things that can happen? The probability and random variables piece comes into play, and that probability, the idea behind a probability, is that we want to assign a real number, we'll denote it probability of A, to every event A in the sample space. So we'll have this notation that we'll use throughout the lecture. This capital PR in italics denotes probability. And there's tons of books written on how to interpret probabilities and what they mean. We're not going to go into those details, but quite simply, we could take a degree of belief interpretation. And so that if the probability of A is large, then that's a measure of strength of belief that A is true. If probability of A is low, then there's not a lot of belief that A is true or A is likely to happen. So probabilities are bounded between 0 and 1. So the closer you are to 1, the more likely that event is true. Probabilities near 0 are indicative of events that are not likely to be true. And so if I go back one slide, A is the sample, A is events in the sample space. And so we could discuss probability in terms of events in the sample space. That's a very, day 2 of statistics and probability approach to probability. That here's your sample space, you've got events in the sample space, let's just assign probabilities to those. But that quickly gets very exhaustive, in that itemizing the sample space for complex experiments can become pretty hard. Obviously, there's no grant funding for coin flips. And so sample space for real experiments are much more complex, and it's then tedious to put probability on every single event in the sample space. And so often what's done is that you'll convert items in the sample space to the real number line, and then discuss probability on the real number line, recognizing that it equates to probability of events in the sample space. So there's a lot of mapping that goes on, and there's a lot of PhD theory that underlines how all the mapping must proceed in order to make sense from a mathematical standpoint. And so I'm going to try to just on a very broad strokes give what those mappings are. And so the crucial link between the sample spaces and the data is going to be via a function, and in particular we're going to call that a random variable. So a random variable is a function that assigns a real number to each outcome. And then at a certain point in most probability courses, we ditch the sample space and we work directly with random variables. And so I think people often forget that piece, that random variables actually are a function, but since we're often only interested in the output of the random variable, we often don't think of the random variable itself as a function. We often just think of it in terms of the output. And so here's an example of a random variable. And we can take, say, poker. And in a poker experiment, you might deal 5 cards, and you're going to, if you think back to the sample space, you would have to fully elucidate the sample space, put all of the possible 5 cards and the order in which those 5 cards are dealt on the table. In other words, write out all the combinations. But the random variable, if you have the random variable X, say counting the number of hearts, then you would take an event in the sample space, and that event, if the input was the following 5 cards and X counts the number of hearts, then X applied to that input would be equal to 2. And so there is the random variable X acting as a random variable in the sense of a function. And now we can simplify all of the events, say, that exist in the sample space. We can think of them in terms of what their output would be for the random variable X. Say we might be interested in the number of hearts, or we might be interested in the number of red cards, or we might be interested in the number of heads, and so on. And those random variables are going to keep track of those. And what's important is this is a number. The output is a number. And so now we can apply probability not to just say the sequence of 5 cards. We can apply the probability to that random variable. So what's the probability that X equals 2? Well, that's now something we can do the mapping and think about the event, not in terms of the sample space, but the event in terms of the random variable. And so examples of random variables you might think might be stuff like yes or no, low, medium, high, Likert scales, where you might have something like strongly disagree, disagree, all the way out to strongly agree. Well, those are categorical variables. Those are not numbers. Those are not on the real number line. And so those are not technically random variables, as they're not recorded on the real number line. However, statisticians can turn those categorical variables into random variables. So we can code yes or no as 0 or 1, or low, medium, and high as 1, 2, 3, Likert scales, and so on. So random variables, a key sort of distinction is that you should think about, am I measuring these categorical variables? I should be clear to say, well, convert them, say, to random variables, but recognizing that a random variable should be a number on the real number line. And so here's an example of something that might be an experiment that I'm more familiar with. Like I said, I work in the gene expression world, and in the gene expression world, one of the most popular genes is in terms of breast cancer, is the so-called BRCA genes. And we might be looking at one of the BRCA gene expression, and we're going to let X denote the number of reads that mapped to a BRCA gene. So we might be analyzing a patient's blood sample, and we want to measure the expression of that gene, and X might denote that number of the reads mapped. And so subtly in that example, we've abandoned the functional aspect of X, and we're just thinking about the output again, that X is going to be that count. And so the extension on that random variable X would now be kind of the next step of, well, we're going to measure that on each person individually. And so we might measure X sub 1, X sub 2 out to X sub n if we recruited n subjects. And so when we have a random variable, we often put that subscript to indicate that we're measuring this on a collection of people. We might also imagine other random variables in gene expression. We don't just measure one gene anymore, we measure tens of thousands of genes. And we should think about each gene in terms of its own random variable. And so X might be for the BRCA gene, Z might be for P10 expression in a given subject. P10 is another well-known gene that's associated with a lot of cancers. And so if you were doing a cancer study, you maybe want to focus on those genes. But the idea would be to note that those are measured and there's random variables associated for those measurements. Now, these random variables are the critical link from the sample space to the real numbers. So in the statistics world, we often use capital letters in the alphabet to denote those. So random variables are functions, but like I said, we only focus on the output. And I think that's the first point that a statistician will talk about with you, at least personally. When I'm working with collaborators, I talk with them and say, what is it that you're going to be measuring in your experiments? And I say it that way, but what I'm thinking is, what are the random variables that I'm going to be working with? Are you going to measure categorical variables where I now think, okay, I'm going to translate those to random variables? What's the order of the measurements? Are they going to be count data? Are they only integers? Can they be positive and negative? Are they continuous? Those are the subsequent questions that are going to come out, but the random variables are going to be the first thing of interest. So what are the random variables that you're going to be obtaining and measuring in the experiment? So the first goal was to convert the items in the sample space to the real number line, and then discuss probability on the real number line. Now we can talk about probability in terms of the real number line. Put another way, we can talk about probability in terms of those random variables. And so we might have, going back to our toy example, we might have the coins, the coin flip example where we had 2 coin flips. We put the random variables, we put the random variable counting the number of heads, and then the events in the sample space, we could think about the probability of that event, or we could think about the probability in terms of the random variable counting the number of heads. So the probability that X equals 2 would be 1/4, because there's only one arrangement with probability 1/4 where X is equal to 2. The probability that X is equal to 1, however, can come out with 2 different combinations, each with probability of 1/4, so those add up to be 1/2. And so you can think about probability in terms of events in the sample space, or you can think about probability of those random variables. And it's once we've established the random variables that we want to measure, now we can put probability for those random variables, with the huge advantage of characterizing the probabilities on the real number line. So if we're focusing on the outcome being a set of values on the real number line, putting probabilities on those can be done in a much more general fashion, as opposed to putting probabilities on events in the sample space. In other words, a statistics textbook, if you were to say, here's the probability of HH, HT, TH, TT in a 2-coin experiment, chapter 2, 3-coin experiment, chapter blah, 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 it becomes too specific. But if you've got random variables where you know the outcomes are on the real number line, now we can use probability distributions that characterize probabilities in terms of those real number lines. And that's the idea behind probability functions, say like the CDF of a random variable, this denotes the probability that the random variable was less than or equal to a particular value. It wouldn't make sense to talk about the probability that HH is less than or equal to some value because those are two letters. But it does make sense that if you're counting the number of heads, what's the probability that 2 is, or the probability that X is less than or equal to 2 has a lot more meaning. And so that's the idea behind why we want random variables. The idea is that now we can use probability models to summarize the data. And so we've done the hard work of converting the sample space to the real number line via random variables. We've learned that there's methods to summarize those probabilities via CDFs. Now there's a wealth of probability models that are at our disposal. And it's the job of the statistician to choose what probability model makes most sense for the data. And so I'm going to talk about a few of the models here. And some of these models you've probably heard of. So the normal model. You might think is synonymous with distribution, and I think that's okay for this lecture, but there's a slight distinction between a model and a distribution. But the idea for a normal distribution is that the random variable X would be taking on values from negative infinity to infinity. If you were thinking about a binomial model, the binomial model can take on values from 0, 1, 2, out to n. And so as a first start, if we go back a slide where the statistician is trying to figure out what probability model makes sense for the data, one of the things they're going to think about is, well, what are the values that this random variable can take on? If the random variable can be negative, it doesn't make sense for a binomial model to exist there, because the binomial model isn't allowed to take on values like -3 or -4.1 and so on. So this type of analysis is what the statistician is thinking about in terms of what model maybe makes sense for your random variables. Likewise, if you're using that BRCA experiment where you're counting observations, if you're using count data, a normal model doesn't make sense. A normal model is allowed to be negative and it's allowed to be continuous. And so if you're using count data, it doesn't quite make sense that a normal model would work there. Probably something like a negative binomial model or a Poisson model might be more appropriate. A count model that has kind of a top end where it can't be larger than a particular value, you might think binomial model. But if you know the count can grow infinitely large, you might think about Poisson or negative binomial. If you know the random variable is only keeping track of one of two outcomes, maybe a Bernoulli model makes sense, where there's only two outcomes, a 0 or a 1. And so these types of models, particularly the values that those models are relevant for, is how the statistician can be thinking about what model makes sense. And so kind of step one, what are the random variables you're gathering? Step two, what values can those random variables take? And then that really is getting at what models are maybe most appropriate. And there might be some disagreement. We might notice that Poisson and negative binomial both take on the same supports, if you will, that they give 0, 1, 2 out to infinity. And so there's other assumptions that would distinguish those two models to try to figure out whether the Poisson or negative binomial is more important. And so it can't just be based on the values it can take. There's other aspects that differentiate these models that are relevant, or that are important and relevant too. So the point of choosing these models, or choosing one of these models, is now we've got the CDFs, or the equations that can characterize the probabilities for those settings. And so if we wanted to know the probability that you're less than a particular value, say little x, we can just plug it in to the CDF for the particular distribution. And we see this introduction now, kind of our first Greek letter, in other words, this theta parameter. And so the other piece to this relationship of in the probability models is that there is a parameter often that's associated with them. So just by choosing, say, an exponential distribution, it's not quite enough. You'd want to know what that parameter is that's associated with the distribution. And that has to do with the inference part that we'll be talking about in a minute. So theta is a parameter. If you're trying to translate statistical sections, the Greek letters are often used to denote parameters. Capital letters denote the random variables. And if we knew, say, theta, then we could talk about the probability distribution. And so that's what distinguishes a model from a distribution. A model gives you a framework for the CDF, but it doesn't give you the value of the parameter. If you knew the value of the parameter, if you had the value of the parameter, now you have a distribution. And so there's a slight technical distinction between a distribution and a model. So what makes statistics useful to understand complex scientific experiments is the multivariate aspect of this, right? As I mentioned, in the gene expression world, we're not just measuring BRCA expression. We're measuring BRCA and we're measuring PTEN. And so now we've got two different random variables, and we want to think about the relationships between those two random variables. We are measuring random variables in, say, a case control study. Some of the people are diseased, some of the people are healthy. That random variable might be 1 or 0, and we want to measure BRCA expression, that count random variable with the 0, 1, healthy, not healthy. And so probability models are useful to us in the multivariate setting, and useful in the sense that that's going to be where we make our comparisons in the experiments. And naturally, most experiments at some point have some kind of comparison that we're interested in. Is the wild type different from the control or the sham conditions and those kinds of things? Those comparisons are done via probability models, where there's the natural extension from a CDF in a univariate or single random variable to, say, comparing multiple random variables. One of the building blocks, fundamental aspects in probability models is linear regression. That is the bread and butter, if you will, for how to compare two random variables. There's obviously many books on linear regression, all of the aspects of linear regression in terms of handling X's and Y's under different settings. What if X can only be 0 and 1? What if Y is a count random variable, and so on. So all of the different flavors for how X and Y are measured introduce all of the different flavors of linear regression that are out there. So you might have heard of a simple linear regression, often where there's a normal assumption. Then there's generalized linear models, where that topic is designed to analyze the relationship between random variables where the normality assumptions are not met. And obviously we can't go through all aspects of linear regression, but the idea is captured often in this equation here, where you're understanding what the relationship between yi and xi are, and the parameter that you're going to be interested in is this beta 1. If beta 1 is equal to 0, then what that says is any values of xi don't influence what yi is. If xi's are just multiplied by 0, 0 times anything is 0. So if beta 1 is not 0, that's where things get interesting. Then it's saying, hey, if you change x1, if you change the xi, then the yi for that person is going to change. So if you're measuring P10 in BRCA expression and your beta 1 is positive, that says, hey, if BRCA goes up, P10 goes up. In other words, there's an association between those random variables, and that might be the kind of thing you want to get at in your experiments. So as a statistician, kind of the next step is going to be, these are the things you're measuring. Here's your probability models for them. Now, what are the comparisons you want to make? In other words, what are the associations you're looking for? And that's going to boil down to some statement about a parameter. And so if it's in a linear regression, that statement is about, is beta 1 0 or not 0 in that experiment? Because if it's not 0, now we're claiming that there's a relationship there. So at this point, there's two problems really holding us back still from fully summarizing the experiments at this point. What model should I choose? So I talked a little bit about that. So what's the distribution there? That's the model selection problem. Oftentimes that question is challenging and it's a little bit subjective, and the statistician might say, here's the model that I'm thinking we should use. But there is a formal discipline or formal theory that can help with the model selection problem. But those details are often not put into statistical protocols. Usually it's, here's the models that we're going to use, or the model that we're going to use. Question 2 is more, in my opinion, more relevant to this discussion. If I had a model, how do I get values or estimates for those parameters? In other words, going back one slide, here's my linear regression model that I want to use. And I've just laid out, or spent 5 minutes laying out, why it's important to know what beta 1 is, whether that's 0 or non-zero. How do I answer that question? I could just take a guess at it, but I want the data to drive that, and that's the focus of inference. So in the statistics part of probability and statistics is, I'm going to use the data to give me an estimate of what beta 1 is. In other words, everything I've done up to this point is probability. I've put the probability models on. I've put a model for what the relationship between yi and xi are. But now I want to go out and I want to gather the data, and I want to come up with an estimate of what I think beta 1 is. And so that latter question, how do I get values for the parameters? How do I get estimates? How do I get guesses? How do I get educated guesses for the parameters? That comes from the data. And that's the focus of inference. That's why you're writing the grant. You want to get the data and you want to make inference. You want to make conclusions from the probability models. And so that's the third bullet point here. So inference or point estimation, that's the idea behind using the data to obtain estimates of those parameters and ultimately make conclusions about the data generating process, i.e. the experiment. So we wouldn't just stop at saying, well, our guess for beta 1 is equal to 1.4. That's not helpful to the collaborator. But what is helpful to the collaborator is to say there's a linear relationship between, say, P10 and BRCA. And in particular, that relationship is such that there's a 1.4 fold connection between how expressed P10 is and how expressed BRCA is in this data. And so that's the translation part about what the estimate of the Greek letter means in terms of what's going on in the context of your experiment. So the context is absolutely important here, and it's the bridging, or like I like to call it, the translation. What's the context in terms of the probability models that has to be translated into the context of the experiment? So that's where we're going to be going in the remainder of this talk. First things first, we need a method or methodology to obtain a guess or a point estimate of the parameters. Given a model for your random variables, a very good recipe for an estimator is maximum likelihood estimation. These estimators have very nice properties and are the focus of a lot of our master's level theoretical coursework in statistics. You might be familiar or heard people talk about Bayesian inference. That's another approach to estimation. You might have heard people talk about method of moments estimators. There's a handful of different estimating techniques that are out there. I'm not claiming maximum likelihood is always the best, but I think maximum likelihood estimation works well in most situations. And so to me, that's always the starting point, and in a lot of cases also the ending point, that you're always going to do okay with maximum likelihood estimation. It might not be the best in your scenarios, and that's something that, again, that we're not going to go into. But I guess what I'm trying to point out is maximum likelihood estimation isn't the only option here, but it's always a good option, maybe not the best. So how does maximum likelihood estimation work? The idea behind maximum likelihood estimation is that it does exactly what the name suggests it does, is that our best guess of the parameter is this MLE, or what we'll call MLE, estimator theta hat, where we're going to try to maximize the likelihood function. So we're getting into maybe a little bit too many definitions for a late afternoon talk, but the idea is you might measure three values, x1, x2, and x3, and you might be interested in the mean functional parameter denoted theta. And an example, an often used example of a maximum likelihood estimator is the sample average. So you just average those three values together to get theta hat. And so there's a translation here as well, where now we're replacing x1, x2, and x3 with what those actual values are. So we've gone out, we've done the experiment, we've gathered the data, 20, 30, and 25, and we're going to average those together, and that's going to give us theta hat. So this notation where we put that little triangle or top hat on top of the parameter denotes that that's an estimate of that parameter. And so the bridge between probability and statistics is that the parameter is more on the probability side, the statistic is the hat, and it's estimating the thing without the hat. It's estimating the parameter. And so, like I mentioned, MLEs are often very popular. Alternatives exist, but we're not going to cover them. But conceptually, the idea is the same. conceptually, I think all statisticians, if I could get away with the generality, all statisticians want to use the data to arrive at a good guess, best guess, reasonable guess of the true parameter. So statisticians aren't in the business of taking pure guesses without using the data. So the statistician wants to make a guess using that data, recognizing it's a guess, but it's an educated guess. It's a guess based on the data, but we don't claim that that's 100% accurate. And we characterize that inaccuracy often with confidence intervals. And so step 4 is translating that probability model's conclusions into data knowledge with a recognition that that knowledge has uncertainty associated with it. We use theta hat, but we need to recognize there could be some error around theta hat, particularly if our best guess was based on only a very small data set. There might be a lot of variability about what the true answer might be. And so that knowledge we can break down into kind of 2 pieces of it. The first piece of knowledge is, what's my point estimator? What's my best guess? What's the particular value of theta hat? The extensions from the point estimator are confidence intervals and hypothesis testing. So confidence intervals and hypothesis testing often go hand in hand, and they're commonly both performed in experiments. And so we'll talk a little bit about both of those things, so both hypothesis testing and confidence intervals. So in hypothesis testing, we start with a null statement about a parameter. So we might start with, e.g., theta equals 0, or for example, beta 1 is equal to 0. Remember, in the linear regression model, we were interested in whether beta 1 was 0 or not 0. So in hypothesis testing, we'll start with a statement, we'll call that H0, and the opposing statement we call the alternative hypothesis, and that's the non-null setting where we just take everything else that can happen. So theta is either 0 or not 0. The alternative is often denoted by this H1. And so now that's framed the question between the 2 hypotheses. Is theta equal to 0 or theta not equal to 0? And we need to distinguish between those 2. So a common analogy, and I think a good analogy, is the US court system, where you're innocent until proven guilty. So you could frame that as a hypothesis test, where the null hypothesis is you're innocent, and the alternative is that you're guilty. Now, what happens in a court trial? You go out, you gather the evidence, you present the evidence, and the judge or jury has to decide between H0 and H1. The same thing happens here. We're going to set up the hypothesis test, beta 1 equals 0 or beta 1 not equal to 0. We've got to go out and gather data, and now we've got to come up with a rule for deciding between the choices. And maximum likelihood estimation has a very nice framework for the rules to make those decisions. Obviously, in the court system, there's not a clear rule of, if you get evidence A, B, and C, then you have to declare guilty, and so on. In statistics, we have a little more rigor in terms of our rules are set up, that given certain scenarios, you make the decision between H0 and H1. And so there needs to be in a hypothesis test, there needs to be a data-driven rule for making that decision. So as an example, you might choose H0 when, say, X is greater than 10. Otherwise, choose H1. That's a very clear rule. I go out, I measured X. If I got a measurement of X greater than 10, then I decide H0, otherwise I choose H1. And so I'll go back one slide, the theory for hypothesis testing is often presented with maximum likelihood estimators, because with maximum likelihood estimators, we have a clear-cut prescription for deciding between H0 and H1. Recognize that when you decide between H0 and H1, you don't know if that's the correct answer. You're making a conclusion, is that person innocent or guilty? But we make mistakes in the court system. I don't want to say all the time, but they do happen. And so same thing can happen here. We're going to use the data to decide between H0 and H1, but that might not be the correct decision here. And then, we have to live with, well, we gathered the data, here's the decision that we made based on the data, but recognize that there's errors that can be made in the process. So I want to try to tie this all together with an example that's not coin flipping and poker and so on. I think those examples are helpful, but they're not as helpful as having an example that's more connected to the world in which I think many of you are operating in terms of grant writing and research. And so in this bioequivalence example, we might be working with a new medication, and the FDA has requirements for demonstrating bioequivalence. In other words, that a new drug is not substantially different than the current treatment. And on the surface, that might sound like an experiment that's not all that worthwhile. But in fact, bioequivalence has a lot of relevance, because new drugs or new treatments might be easier to tolerate. In the cancer world, some treatments can have pretty drastic side effects, and so you might have a new drug where the side effects are more minimal, and so you want to demonstrate that that new drug is as effective as the current treatment. And so side effects might be a reason for showing that this new drug is as good as what we've got out there. There might also be a patent issue where here's the generic drug and you want to show the generic drug is as good as what's out there. And so there might be some financial or resource-based decisions to show that the new drug is as good as what's available. And so there's a fair amount of settings in which bioequivalence is relevant. And so we might give 8 subjects, in this example, using medical patches to infuse a hormone into the blood. And each subject might receive the 3 treatments. So you might get the placebo patch, the old patch, and the new patch. And so you might be measuring some kind of hormone amount in the blood. Again, the statistician would want to spell out what is it that you're measuring, how are you measuring it, and so on. And in this example, we have the 8 subjects and their measurements, and you might be interested in obviously what the original measurements were, but the obvious comparisons of interest would be, how does the old patch compare to the placebo? In other words, is the current treatment effective compared to a placebo? And then how does new compare to old? And so you might want to compute new random variables from your old random variables, or not necessarily old, but your random variables for placebo, old, and new. You might want to create new random variables looking at their differences. And so those bioequivalence random variables, if we go back to our four-step process, we're going to measure new, old, placebo. Those are going to be random variables that are mapping from, say, some immunoassay sample space to the real number line. So notice, obviously, on this previous slide, we have numbers associated with those measurements. So those are the outcomes from those random variable functions. And the sample space, say in immunoassays, it might be some kind of photon measurement of a labeled antibody and so on. So I am always cognizant of the fact that random variables are functions. And I think about that function to the real number line is coming from some mapping of this sample space. And so that understanding that mapping helps me to think about what the values are and what the relevant probability models are. So notice, going back here, placebo, old, and new, those are all positive numbers and they're all integers. So I'm not necessarily thinking about 0-1 types of probability models for that data. When I look at new minus old, I see some negatives and some positives, and the negatives are pretty large negative and the positives are pretty large positive. I might be thinking about a normal distribution, but also recognize I might want to think a little bit harder because these are integer values. So those may not match exactly with a normal distribution where the idea is that the values can be continuous. And so there's a famous quote out there that all models are wrong, some are useful. The normal model on one hand might look wrong for new minus old, but it might be useful in still analyzing that data. So we recognize that, yes, you can't have a minus 1200.1, which you would in theory expect with a normal distribution, but we live with the approximation of the normal model to data like that. So our random variables of interest might be, say, Z and Y, and Z is the old minus the placebo, and Y is the new minus the old. So those two random variables are going to hopefully capture whether or not old is effective and whether or not new and old are about the same. And so the FDA has guidelines and requirements to demonstrate bioequivalence, where they're going to say that the requirement for bioequivalence is that this value of theta, an absolute value, has to be less than or equal to 0.2. So that's the mean. The theta is defined as the mean functional for model of Y. In other words, what's the mean parameter in Y compared to the mean parameter in Z. In other words, the mean parameter for Y divided by the mean parameter for Z. If theta is pretty small, in other words, if theta is close to 0, then what does that mean in terms of the fraction? If theta is near 0, that means the numerator must be near 0, and the denominator can be far from 0, right? If you have something small over something not small, then you're going to get something close to 0. And note that's capturing exactly what we want, because Y is new minus old. So if the mean for Y is near 0, that's saying new and old are about the same. Whereas the denominator can be large, where that's capturing that old and placebo are actually far apart, which is what you'd want. You want old to be effective compared to placebo. So you want that denominator to be large, and you want the numerator to be small if your new drug is equivalent to the old drug. In other words, if you've established bioequivalence, it makes sense that you'd want this quantity theta to be small. So that's kind of the modeling piece. theta is the model that we want to study, and we want to estimate theta, or we want to make inference on theta. So we're going to go out, we have those 8 subjects, we're going to compute theta hat by its maximum likelihood estimates. Turns out, again, we can just take sample averages. And if we looked at the average of the y's divided by the average of the z's, then theta hat turns out to be minus 0.07. And if our hypothesis tests, if we remember how we want to set up our hypothesis tests, if you want to demonstrate bioequivalence, your alternative is that you want to show that theta in absolute value is less than or equal to 0.20. And so if you can demonstrate that, then you've established bioequivalence. Our estimate is minus 0.07, but we have to integrate our kind of testing rule around that estimate. In other words, the testing rule has to build in our estimate of the variability. And so a testing rule from maximum likelihood estimation might be something like this. In other words, the testing rule has to be a data-driven rule, and it's going to be that we could reject H0 when theta hat minus this quantity is greater than or equal to minus 0.20, and theta hat plus that quantity is less than or equal to 0.20. So we go ahead, this is a data-driven rule, meaning once I've gathered the data, I just check and see what happened. Well, remember my theta hat was minus 0.07. Minus 0.07 minus that quantity turns out to be minus 0.28. Well, minus 0.28 is less than minus 0.20, and so we do not reject the null hypothesis. In other words, I needed that quantity to be greater than or equal to minus 0.20, and minus 0.28 is not greater than minus 0.20. And so we don't reject H0, and so we ultimately conclude that this experiment has not demonstrated bioequivalence. And that is potentially a little bit frustrating because your point estimate was minus 0.07. So your point estimate was suggestive of bioequivalence. In other words, remember bioequivalence is that theta in absolute value has to be less than or equal to 0.20. Theta hat is less than or equal to 0.20 in absolute value, but once you build in the uncertainty, and again, we don't have the time or really the time to establish how to create these testing rules, but the hypothesis testing rule, even though the estimate suggested bioequivalence, once you build in the uncertainty, you lose that bioequivalence conclusion. So we conclude that this experiment has not demonstrated bioequivalence of the drug. One of the things that the statistician will be thinking about, and I think a topic of one of the later talks, is what if I were to have gathered more data? In other words, this is a pretty small study that only had 8 people. If I had had 25 people, would I have been able to establish bioequivalence there? And so the concept of power is exactly dealing with this question of the point estimate looked like it was bioequivalent, but when I took into account the uncertainty, it wasn't the case that I could conclude that. However, if I gathered more subjects, I might have a less uncertainty associated with my estimate and then be able to conclude the other direction. Think back to that analogy of innocent till proven guilty. This might be a scenario where the person was guilty. However, I just didn't have enough evidence at the time to really make that conclusion. So this is an example of an experiment where you'd potentially want to get more subjects, more evidence here to make a definitive conclusion here. And so in a way, this experiment concluded what we originally assumed. We had to assume innocent, and we don't have the data to conclude otherwise. So does it mean that the person's really innocent? We don't really know. So there's the journal world. If you're publishing in a journal world that relies on statistics, they don't generally like to publish results where the conclusion was H naught, because the conclusion of H naught is the conclusion of, here's what we assumed, we did an experiment, and we don't have any evidence to not retain that original assumption. And the reason is, did you not gather enough data, or was the original null assumption the correct one? And so because it's harder to tease out that question of, you might be stuck with your original assumption just because you didn't gather enough data. That's the idea of how to properly power your experiments, and as a topic for a subsequent lecture. And so the conclusion of that bioequivalence test is that we've got to translate that hypothesis test result into what the drug conclusion is. So by accepting H naught, we have not demonstrated bioequivalence, and so we conclude the two drugs are not equivalent, or at least we don't have the data to support the two drugs being equivalent. And so back to the Judge Wapner write-up part of this, we should be thinking exhaustively in terms of writing as much as you can about what it is you've done or what it is you're proposing to do. Then we can scale back. If the journal says this should be, smaller in length, or if the grant only allows for a limited space, then we can cut back. But I'm a staunch believer in the more detail you put into the stat methods, the more better off you'll be. And then if you need to scale back, you can scale back. But if you have that fully detailed description, that's going to be the more useful document in years to come, say if that grant gets funded down the road. And so what's going to be important? What are the ingredients that they're going to look for here, or that the statistician should be including? So how many people did we recruit? Well, we had 8 subjects. What was it that we measured? We recorded the level of the hormone infused, and note, you could still nitpick my right up here in terms of, well, how is that thing measured? What were those units? We had the 3 treatments. We consider each treatment as a random variable mapping from the sample space to the real number line. What are the random variables that you were interested in? So we created Y and Z. We could make some assumptions about Y and Z, that they're a normal distribution model. How did you estimate the parameters in Y and Z? So we use, say, maximum likelihood estimation. What's the hypothesis test you were interested in? Well, we were interested in testing bioequivalence. And what was your conclusions? I think with this framework, this is the kind of detail that grant reviewers are looking for, stat reviewers for journal submissions are looking for. What are their random variables? What were the models that they used? How did they estimate the parameters in the models? What was the test? How are they going to make the conclusions? Or if they've already gathered the data, what were the conclusions? And so that's the kind of thing to think about in the write-up. This is a little bit of a recap, and I put the peanut butter and jelly sandwich there because I remember at one point in elementary or middle school where teachers said, oh, write how you would make a peanut butter and jelly sandwich. And you could say, oh, you just take 2 pieces of bread, put peanut butter on one slice and put jelly on the other, and then combine them. Other details are, I go to the knife drawer, I open the drawer, I take a knife out, I walk to the cabinet where the peanut butter is. I open the cabinet door, take the peanut butter out, walk the peanut butter back. And so the exhaustive plan, I'm not saying we should include every possible detail like the peanut butter and jelly example, but the more details you can include, the better. That clear writing is clear thinking. So if you've got all of those details there, that's the piece that's the most useful. I fully recognize you have to trim those down for scenarios and journal writing and grant submissions, but to have the full document is helpful and the most useful. So clearly, what should be in there? Clearly, precisely define your random variables, the models, the hypothesis tests. Where and how is that data going to produce those random variables? How much data to obtain and design? Again, that's the sample size power piece. One thing I didn't talk about but should be included is what's the stat software used to implement these tests. And so you can say maximum likelihood estimation and so on, but in this day and age, are you using SAS? Are you using SPSS? Are you using Stata? Are you using Excel? Are you using R? What's the software that you're going to use? Again, that conveys that you're fully thinking about how this data is going to be stored and analyzed. I'm also a firm believer in writing in one voice, striving to write in one voice, where the random variables have that mapping back to the language in the experiments. So meet with your collaborators, meet with your statisticians, and make sure that the stat section doesn't look like a cut and paste. Is it clear that X, Y, and Z, the random variables that they're talking about, are expressed in the language that's used in the experiments as to how they're going to be measured? And likewise, the stat conclusions and hypothesis tests should be translated into the experiment as well. And that one voice piece is critical. It's not something that's easily accomplished over email. Say, I think it's communication via meetings or Zoom meetings, however you want to coordinate that, but that communication to create the one voice messaging often works best when there's regular meetings with statisticians and their collaborators and or the research team. And like I said, these things might have to be trimmed later. And I can't tell you how many times I've read the trimmed piece and said, boy, I don't quite remember what I was thinking there. But then I go back to the full-blown version that I had stored as the rough draft, and I say, oh, now I know exactly what it was that I was going to do in this section. So here's some references to some materials. The last reference, if you're interested in learning about statistics with not all of the mathematical rigor, I think all of statistics is a good starting point. And so I'd recommend that. Other references that are out there, I think the internet is a great source for tips to write stat analysis plans. This is one I pulled from the American Statistical Association, that there's tips out there. And so here is our last slide of the day, where there's the portal for CTSI services. And so if you go to the link at the below, you'll find there's our services menu and there's the BERD. And so if you are looking for collaborative help on grant submissions, particularly on stat or biostat side, the BERD portal is there. And there's our core director, who you can also contact if you have further questions. So with that, I'll stop and take any questions that you might have.